Thank you. Thank you, Wojtek. It's a great pleasure for me to be here, and I'd like to thank you all for coming out in the rain. I hope I'll make it worth your while. I have to stay over here because my clicker's got limited range, but that's what I do. And if you need to hear me in the back and need me to put on the mic, let me know, but I'll try to go without it. I'm going to talk about, that's my title. I'm not going to try to justify the title just yet, maybe in questions afterwards, but let's see if we can get, I got to get on this side for my clicker, huh? There we go. Okay, first thing, I'm going to be talking, I think, about a personal opinion. Now, I've done a lot of things and been a lot of places that have helped formulated this opinion over the years. As Wojtek pointed out, I've written some books. I'm work in Silicon Valley. I've done some software engineering. I've done some mathematical research. And all of these activities have underscored what I think is a really important fact, that scientific method is really essential in applications of computing. Now, I put this slide up because I've talked to a lot of people over the years about this opinion, and actually hardly anyone ever disagrees. So maybe this is some kind of actual consensus. But still, I think there's a problem. And the problem, I think, nowadays is that, first of all, there are plenty of scientists who don't know too much computer science. And the converse is also true. There's plenty of computer scientists who, that should be say, lack basic knowledge, sorry for the typo, don't know too much science. In the early days, in the 70s, everybody took the same intro course. There was only one computer. If you wanted to know how to program, or if you had any application at all, you took the Intro CS course. So scientists and computer scientists were all in the same course together all the time. In fact, a lot of designers of computers and so forth were initially scientists. A lot of the applications were scientists. Somehow we've lost that a little bit, and there's a lot of attitude among particularly entering students that intro computer science really isn't for me. It's just if you're going to be working in a cubicle somewhere. And actually, there's some reinforcement with that in the curriculum at many places. Now, I'm not being critical of any particular curriculum. I don't know details. I'm just saying this is a general feeling that I think a lot of people have. There's general dissatisfaction with the introductory computer science curriculum nationwide, say, to pretty serious extent by comparison with, say, introductory curriculum in economics or physics or chemistry or biology, where there's broad consensus about what should be done. So I'm going to talk just briefly about a way to address the situation where we try to go back to the situation where everybody's in the same course and try to catch all students with a general interest in science and engineering before they really know what they're going to wind up doing, as opposed to the current situation where they kind of decide first and then educational institutions have to react by teaching computer science for physicists and computer science for engineers and biologists and so forth. So that's what we've managed to do at Princeton over the last several years. I have a new book out that is a part of this activity. But the basic idea, and there's a website, please go visit the website if you're interested in this at all. There's a basic idea that all students, really, I think this should be like even high school students, but let's say beginning college students, should learn modern programming models. They should learn the scientific method, particularly understanding program behavior, because it matters. They should learn a lot of basic concepts in computer science. They want to know applications. And basically, they want to be prepared for engaging with computation, because all of them, no matter what they decide to do, are later going to have to deal with computation, whether they're going to be working in a cubicle or whether they're going to be working in a scientific lab or in a financial institution on Wall Street. So that's what we wanted to try to do, and we've had some success with it at Princeton. We have the same intro course. Most of them take it in the first year. And it's got all these things. The basic goals are demystify computer systems, empower the students so that they can know how to exploit computation, and to build some kind of awareness of what's important in computer science. Now, this is a prelude to my talk. This isn't really the topic, but it's a good basis for what I'm going to be talking about. And I want to try to do this. Let's see if I can get this thing working. So what we do, besides covering that material, what we try to do is draw examples and assignments from familiar real-world applications. And this is just one little spectrum of how much you can do with a reasonable programming model with a pretty simple concept. Now, I think I've lost control over what order these things happen. Yeah, so I'll just get them all going. There we go. So the little one, that we do like in week 2. So we've given just the ability to draw a dot on the screen, you can figure out how to make it move and how to bounce. You hit the wall, you reverse the y coordinate, that's about all you have to do. Hit the vertical wall, y coordinate, horizontal wall, x coordinate. So that's a first lesson. That's a programming tool, good graphics. And then, want to teach object-oriented programming? That's a perfect example. Those are all instances of a ball object with one piece of code. I think I can get this to keep going. It's more fun. Let's see. Yeah. Oh, maybe not. So those are instances of a ball object, and there's very little code to make the multiple balls go. But then, of course, the first thing the students say is, well, what happens if they collide? Well, that's this one over here. Actually, we don't do that one until the sophomore course. I'll talk about it. More interesting one is the one in the middle. So that's Newton was trying to figure out equations of motion of 3 bodies interacting with gravitational force. You see this simulation going, you can understand why he couldn't do it. Orbiting planet switches the one it orbits around. It's got very unstable, chaotic behavior. No way you're going to have mathematical equation for that simulation. And not only that, we can generalize that to get multiple bodies, again, without changing the code at all. Once you get this working, then the code to do 100 bodies and planetary interactions of all sorts is easy and interesting. And it's not much code to get this to happen, really not much at all. All of our students do this in the first year before mid-semester. Not only that, oh yeah, so what happened to it? Well, there's something wrong with the model there, isn't there? Let me go back. Like I said, I lost control of it. Okay, but this one, how do you get this to happen? Well, that's actually Bose-Einstein model, and that's interacting particles. There's no gravity, but if you want to compute things like pressure, you count the number of times they hit the wall. But how do you do this for millions of particles? That you need to have good algorithms. You can't do this without a priority queue algorithm or something similar that can get the calculations done, save basically a factor of n in the calculations. So with this one simple model up here, we're able to cover lots of interesting applications that are relevant and important to students. So not only do we get the science students learning some basic computation, but also we get the computer science students thinking about the scientific method and about performance. Okay, let me get there. The basic lesson for all of them is that nowadays performance matters. That you've got all kinds of applications where your number of inputs are in the millions or billions, and therefore you cannot be using a quadratic algorithm, because a billion squared is 31 years even if you can do an operation per nanosecond. In order to make these applications compelling, we're going to be doing for big amounts of data. And even if you want to do image processing, you can't be using a quadratic algorithm. Students learn that right at the beginning. And so we look at like simple tests. Okay, performance matters. So what am I going to do about, what do I know about performance? There's simple things you can do. If you're running a data-driven program that takes a lot of data as input, you can measure its running time, then double the number of inputs, measure the running time again. So you do that, T of 2n, is divided by t of n. If it's quadratic, that ratio is going to be 4. If it's linear or n log n, it's going to be 2. And that's extremely easy to notice. Run your program, just double the number of inputs, put a loop around it, double the number of inputs each time. If it starts to get twice as slow, then it's not going to work for millions or billions. We teach that right at the beginning. Unfortunately, many, I know from experience, many practicing software engineers and scientists don't even know this basic fact. And they write programs that are quadratic and send them out into the world, and it's not until the customer gets it that it turns out to be slow, or until the actual data is being analyzed that it turns out, well, we can't do it that way. And what do? They look to buy a bigger or faster computer or new application, when actually it's a simple matter of paying attention to efficiency at the beginning and being sure you can understand it. Now, I don't want to be preaching, so what I'm going to do now is talk about a personal experience that I think highlights this, and this is going to be the lion's share of the talk. We're going to be talking about addressing a basic problem, a research problem in algorithms, where the scientific method really plays a role. And I'm going to claim that if you're trying to design an algorithm and you don't run experiments, you're not going to be successful. And if you're a software developer and you just ignore costs, there's going to be a catastrophe somewhere. And I'll try to make that case in this example. Now, there is a preliminary hypothesis that I'm assuming. Let me get in this side because I'm going to be clicking a lot. Grab some. Always get pushback on this from people who develop large software systems. And they say, well, large software systems, it's all about a huge number of modules that interact. And so what you're talking about this performance stuff doesn't really matter at all. But I think almost a huge preponderance of situations, let's say, there's bottlenecks. So first of all, we're taught that building a huge system, you have to break it up into little modules that you have to understand independently. I'm going to claim you better understand their performance independently. If their performance doesn't matter, fine, but there's always a few where the performance critical code resides. And you better understand what those are and what to do about it. I haven't checked this by running Microsoft Word and looking, but plenty of examples of large software systems where bottlenecks reside in small modules. So that's what I want to focus on. I have a small warm-up. I want to make sure I don't run out of time in this. This is a familiar one for many people, and that's random number generation. So all kinds of software systems nowadays have built in this basic concept of you need a program that generates random numbers. So let's look at that in terms of the scientific method. So there's a well-understood model for what it means to be a random number from classical probability statistics. And so let's just take the simple hypothesis. We want the frequency values to be uniform. So we want each value to be equally likely to appear. Let's say they're integers. But there's an experiment you could use to check that hypothesis, and that's generate the numbers and check to see if you got each frequency the same amount of times. But that's a lousy experiment because this program over here that just generates the numbers and cycles through them, that's going to pass that test. Generates each number the same amount of time. But we look at them, we don't think they're too random. So you look at a more complicated, this is a linear congruential random number generator out of a book. And you say, well, that one, it looks more random to me. But if you develop a more sophisticated test, like say the chi-square test, and that checks the frequencies that you actually get against a so-called chi-square distribution that says that according to classical laws, some things should appear more often and other things should appear less often. This one flunks that test. So it's not any better than the other one. They're not behaving like random numbers. And people are still studying what do we do to get numbers that are going to behave like random numbers. It's extremely important. There's applications where it really matters. Like cryptography is a great example, and there's core issues in the theory of computation related to this. So even the simplest thing about generating random numbers, the scientific method matters. And just because it relates to something I'm going to talk about later, here's a more sophisticated test even than the chi-square test. Probability and statistics gives us all kinds of sophisticated models. It's been studied for 100 years. We might as well take advantage of some of that knowledge. So there's the birthday paradox. So you're all familiar with that. You have up to 24 people. After you have 24 people in a room, then 2 of them have the same birthday. And we can analyze that and prove mathematically that if you have random numbers, the average count of generated until you get a duplicate is square root of pi v over 2. And I'll talk a little bit about that analysis. So if you want to know if your numbers are random, you can try this test. Generate them and see if you get the count close to square root of pi v over 2. Or do that a lot of times. We even know the full distribution of the birthday paradox. That's totally different than the chi-squared test, and that's a stronger test. And actually, what people do who really care about getting random numbers is run scientific tests against all these different types of hypotheses to try to check that it's random. As in science, you're not going to really know for sure that they're random. There's no such thing, as von Neumann would say. But at least you can get numbers that have many of the same properties of random numbers. Okay, so that's my warm-up. Let's apply the scientific method when we can. All right, so now I'm going to go into this personal story. So this is just the basic idea that I was writing my algorithms book on graphs, and I knew that there's a fundamental operation that we want to understand having to do with finding a path in a graph between 2 points. It's a fundamental operation, and we want to understand what the story is with that operation. Now, I'm not going to, first I'm going to say this is work in progress. I'm not going to present finished results on this. My point is to kind of present this as a personal story, why the scientific method is important when you're working on problems like this. This is a hugely important problem that has lots of applications. I'll talk about some of the applications later on. Even if there weren't any applications, I think this is a problem to work on. I'm not arguing against basic research. I'm arguing for doing research properly. So there's lots of things I would like to do in terms of applications related to this work I'm going to talk about. I haven't done any of that yet. I'm just trying to understand what's going on here. So it all started for me when as I mentioned, when I was writing the graph. Sorry about that, TV audience. I'm writing the graph algorithms part of my book, and I'm trying to study max flow algorithms. So without going into the details, so max flow is a paradigm where we've got a graph with weights. You can think of it as modeled as pipes with capacities, and you're looking to fill up the pipes with material flowing from top to bottom such that the flow from top to bottom is maximized. And the way that we do it is we find paths from the top to the bottom, fill them up, and then start on the new network with that one path filled up. And just in a loop, finding a path from top to bottom. In this algorithm, in this schema, this is a Ford-Fulkerson schema, it doesn't matter which path you use, just any path at all from top to bottom goes. So there's lots of different approaches that have been thought about. I'm just going to talk about 2. One thing you could say is, I want the shortest path from the top to the bottom. Another thing you could say is, I want the one that pushes the most stuff through. Those are 2 different algorithms. In my series of books, I'm trying to advise people on which algorithms they might consider for various applications. And I'm going to have them both in there, and people are going to say, which one should I use? Which one's better? Kind of interesting to know which one's better. There's certain key steps that we have to talk about. Like one is, how many times do you have to do this? The other thing is, what's the cost of finding each path? So in order to analyze the Ford-Fulkerson algorithm, got to do this finding path thing. And the way that I do my books, which has worked extremely well for me, is to essentially write what I think the story is on the basis of everything that I've read and published and so forth, get some implementations going, and then only at the very end, and I kind of get in my head what I think is going to happen, but only at the very end do I actually run the experiments, and then kind of fill in commentary around what happened with the experiments. Because usually I figure I can get a pretty good idea of what's going on. But in this case, I was definitely wrong, so let me show you what happened. There's So I want to compare the performance of these two algorithms. So there's a bunch of parameters. There's how many vertices are there in the graph, how many edges, and then another parameter that comes up is what's the maximum capacity edge or pipe in the graph. And so just how many times do you have to go through for these two different things in order to get the maximum flow? You go to the research literature and you'll find these worst case upper bounds published for these two different algorithms. And these are early on in the 50s, say 50 years ago. And those are worst case upper bounds on what happened. And people say, well, these look like it's too high. And then how many steps do you find each path? Well, to find a path like the shortest path, the worst case is you have to look at all the edges in the graph. And so worst case upper bound, you multiply those by E. And there's a huge literature on trying to find algorithms that have lower bounds than these. Huge literature, still going on. But these are worst case upper bounds. So I have a sample graph. And I say, okay, I always like to show simulations of my algorithms running on a sample. And so I came up with this sample graph, which is a well-known graph model where vertices are random points, and for a given parameter, each vertex is connected to all the ones in a neighborhood of that vertex within a fixed distance d of that vertex. And if you make the fixed distance big enough, that gives this connected graph. And then I assigned it random weights within a range to those edges. So how many paths? So the worst case upper bounds tell me that these numbers. That for shortest path, it's either 177,000 or 17,700, depending on, so it's the best of those two. So in my case, I didn't assign the capacities high enough, so maybe it's 17,700. And max capacity, just for this graph, 26,575. And how many steps to find each path? 2,000. Okay, so that's the best I've got in terms of performance from these algorithms from 50 years worth of literature. So now I run it on this graph. So what do you think happens? The actual cost for max capacity was 7, not 26,575. The actual cost for shortest was 37. Actual number of steps for each path, 20 on the average. The total is a factor of 1,000,000 high. That's unacceptable, I claim. And that's when I came to say, we really have to do better than this. You cannot be using worst case upper bounds to compare algorithms or to predict performance. That's incorrect. That's wrong. Cannot be doing it. It doesn't mean anything. The worst case upper bound in this case said it would take 26,000. It only took 7. I'm not interested in the 26,000 in this case. I'm interested in the 7. Which one actually is going to be faster in a practical application? Unfortunately, there's a huge literature out there which either implicitly or explicitly is trying to compare algorithms based on worst case upper bounds. That's wrong. It's very difficult to get this point across, even to experts. So the lessons just from that little cut, and I'm doing a whole book on graph algorithms, and this is like the first one, that worst case performance bounds are the standard, but they're not useful for trying to predict performance or to compare algorithms. And what's the working programmer who's trying to apply these things to do? So my answer is we've got to do better. The actual costs are down here. The worst case bounds are up there. What those worst case bounds are is not relevant to what's happening down here. And what's happening down here might be critically important to me. And as this is just an actual conversation that I had with a famous computer scientist. You would all know the name. Recently, said in a talk, well, I have a bad algorithm A, and I have a new algorithm that really Google should be interested in because it's better. And I say, well, what's the matter with algorithm A? And the person would claim, well, it's not optimal. There's an extra log n factor in the running time of algorithm A, so it's bad. And I'd say, but Your algorithm is extremely complicated, 20 pages of details. No one would ever implement it, number one. Number two, log n is less than 6. Number three, it's just an upper bound. Certainly, algorithm A is going to run 10 or 100 or 1,000 times faster than algorithm B in any conceivable practical situation. Why do you say that Google should care about it? And the person rethought his position and said, well, I like it. I don't care about Google. And the sad thing is, I think most people in the room were on his side, not on my side. And I think that's a problem. Okay, so let me go a little bit further now. So maybe I'm just going to press on. So finding a path in the graph. So, well, now what about algorithms? Well, actually, there's plenty of basic algorithms for dealing with this problem that everybody knows. And I'll talk a little bit about implementing these algorithms. There's breadth first search, find the shortest path. Depth first search, which is a 5-line algorithm. There's a famous union find algorithm that you can do with 2 passes. All of them are equivalent from worst case upper bound point of view because they process E edges in the worst case. But for, and there's a problem that there's a lot of different kinds of graphs, and that matters too. But I hope I've convinced you that worst case analysis is useless for predicting performance. So let's try to figure out what we can recommend. Breadth first search, depth first search, or union find. What's the deal? Well, the only way to deal with it is to code them up and run them, at least for the start. Now, we do need a graph model. And I have to say, I'm putting up slides here, and each one of these slides is like 3 months, and then, oh my God, you know, everything I discovered, it's like, oh, that's obvious, you know, you're going to have to deal with that, and I'm going to go through a few steps like that. So you do need a graph model. So actually, I got started pretty early on grid graphs because that's a model I could get my head around. It's still interesting. So that's the one in the middle where you just have checkerboard connected. I didn't even think about applications at this point. At this point, I'm saying, okay, what's the best? Breadth first or depth first on this graph? I don't care whether it's applied. What's the deal? It's nice because it's scalable. And you know, that means it's pretty easy for me to double the size and multiply by 10 and everything like that. And I even naively thought that there might be some potential for analyzing what's going on. Now, I'm using that graph model, but I'm not going to write code that knows that that's the graph model. I want to write code that works for all graphs, and then I'm going to give it grid graphs and see what happens. I'm at least keeping myself general to that point. If you know that these are points, you know the geometry of the situation, you can do better, for sure. After I get into it a while, I realized that grid graphs actually are widely used for huge data. So one example is the percolation model from statistical physics. Oh, yeah, there it goes. So that's where you've got black means it's blocked and white means it's open, and then you put some fluid at the top and it percolates down to the bottom. And if the probability of being black is P, you know, turns out to be a threshold. What's the threshold below which it'll definitely flow, above which it definitely will not flow? And that's studied for that grid graph in the middle there, and for huge instances, could be millions. And image processing, you use it every day. I went to India, the sky was too gray, so click it to make it blue. That's flood fill. All they're doing is running depth first search on a grid graph to do that. So that's just 2 examples. And they do much more sophisticated calculations in image processing, even using max flow on a grid graph where the source connects to all the pixels and the pixels all connect to the sink. They do max flow on that for certain image processing. There's many, many, many other applications of grid graphs, just in case anyone needed applications. But let's get back to the basic problem. So what's best on this graph? I'm trying to set this problem up in the simplest way I know how. So I've got m by m things, so there's m squared vertices, and then there's about 2 m squared edges in this graph. And scales really easily, getting up to millions of edges very easily. And for cost measure, I'll just say, how many graph edges do you touch to find your path? And my problem is, I don't care what kind of path it is, any path at all. and I'll be happy with it. That's so what's the best algorithm under that measure? So that's the experiment that I set up, and now breadth first search, depth first search, and union find, I can code those up and run them. We'll see what happens. So that's the deal. Okay, so this is just railing about the literature being no help again. I thought there's a huge literature. There's thousands of papers about processing grid graphs, and none of them say what to do, as far as I can tell. Okay, now this gets now into the software engineering. Actually, coding up this experiment in a rational way really is a software engineering problem. So I just want to make sure, I'm sure most people are quite familiar with these, just want to make sure we're using the same words. So there's clients, interfaces, and implementations. I want to have an interface that specifies the operations that are allowed. I want to have clients that use that interface, and then I want to have implementations that actually implement the operations. And in this case, I'm going to plug in 3 different implementations of the find the path in a graph code. And the client that's doing the experiment is not going to change at all. The implementation should not be tailored to any particular client, should work for all clients, and then we're just going to test it out for the client at hand. That way, we can solve other problems, we can try other experiments and so forth, and have control over things. So a good data abstraction is good for running these kinds of experiments for sure. So I've got code. It's not that much code for people who are worried about code, and it's enough code for people that know it. So let's just quickly get through this. So the first thing we need to do is implement a data type for graphs. So that means specifying an API, and then actually first thing I usually do when I specify an API is first write the client code to make sure that it's useful, and then we'll worry about the applications later. So in this case, the API that I want is, first I'm going to say the usual model that vertices are integers between 0, v minus 1, if there's v of them, and edges are just pairs of vertex, and I have a little API for edges. For my graph, I want to construct a graph from an array of edges. I want to find a path in that graph, and then I want to get the path that it found back. And I have the simplest implementation that I could come up with for this, and I can do better with modern tools, but anyway, this is the type of client code that I'm talking about for grid graphs. So if I have that implemented, then I can write this kind of code down here to build a grid graph. So what this for loop is, and I'll talk about that in just a second, is just creating new edges and putting them in the array A. And then down at the bottom, call the constructor to create a new graph, G, and then call find path on that graph from source to the target vertex, and then print out the path. And I'm going to leave out the code for finding the path. It's just for every vertex, it gives the previous vertex on the path. Okay, and so that's the client code. And then what's the client code got to do for my particular model? Well, I have to do a little arithmetic. So I have a grid graph. I'm going to number the vertices from 0 to n minus 1 like that. And then I'm just going to go through for each possible vertex, like one in the middle. I'm going to make a new edge from I to I plus m, I minus m, I minus 1, I plus 1. That's what that code does. Okay? And then I have to worry about the border conditions so I don't do edges on the side and everything. But anyway, that's good client code that creates a graph corresponding to that model and then runs find path on it. Okay? With me so far? So that's the implementation of the graph data type. And now I'm not going to spend a lot of time talking about the algorithms. These are basic algorithms for solving this problem. Depth first search is a recursive algorithm where to do a vertex S, you recursively call yourself for all adjacent vertices that aren't marked. And that's depth first search. Breadth first search is different. It finds the shortest path using a queue. And union find is based on set union operations. I don't have too much time to talk about each of these things, but I'm going to code these up. And they're in every basic algorithms course, if not earlier in the curriculum everywhere. Okay, so here's a standard implementation of depth-first search. We say, well, the graph could be huge, so we're going to use adjacency lists. So that's a vertex indexed array with a linked list coming off each node, giving the vertices that are adjacent to it. That code up there takes the array and makes the list corresponding, the adjacency list corresponding to the array. There's two representations. This is all basic algorithm implementation of depth-first search. And then the implementation is, down at the bottom, is the implementation of find path. So it creates an array of marks that are visited, and it recursively calls itself to go from the source to the destination. The recursive implementation, if you're there, it returns. Otherwise, you mark it, and for everybody adjacent, you go through the list, and if it's not marked, call yourself recursively. Okay, depth-first search. So now we're down to actual code. And this is my first, oh my God, I've been working for 25 years in this field, and I can't believe I didn't know this. And what this is completely bogus as an experiment. Why? It looked like good code. I went through it all. Why is it bogus? It's bogus because the cost depends on the client code that built the graph. Think about it. If I start at S and I put in those edges in the order, say, west, east, north, south, what's going to happen? I start at S and I'm going to go west, west. And I can't go west. I already went east, so I'll go south. Then I'm going to go west like that. I'm actually going to hit the whole graph if I happen to put them in that, or if the client happened to put them in that order. If the client put them in south first, boom. So that's off by a square root factor, depending on the client code. This experiment says that if you've got a graph model and you don't know the representation, you can't know anything about performance. Well, first of all, that's a huge problem with the implementation, because a client can do stuff to completely screw the performance of the implementation. That's not good software engineering, is it? So, and I discovered this after I've written the books on graph algorithms. Run a lot of graph algorithms, written a lot of graph algorithms. I don't trust anything anybody says about performance of their graph algorithm if it's got this property. Absolutely not. Even if they ran a lot of simulations, even if they ran the thing a lot, if I can write client code that squares the running time, that's not good. What they're saying is not helpful to me. There's a fix, and it's not that difficult to fix, but I think it's absolutely required for any graph processing algorithm. You're not going to find this fix. You have to look pretty hard in the literature to find it. You can't say to the client, oh, just randomize the edges, put them in random order and everything will be fine, because that's bad software engineering, right? You can't put requirements on the client. I studied for really a long time what it meant to randomize the edges, and I couldn't even come to an understanding of that, because you remember there's two representations of each edge. U is in V's list and V's in U's list. And so putting the edges in a random order, you don't get all possible lists with equal probability. It's not the same as randomizing lists. So I couldn't even understand what it meant to randomize the edges. But what I've come to decide is that at least what we can do to protect against these performance problems, and also to hope to develop an understanding of what's going on, is to use a randomized iterator. So that is, all the algorithms are based on the operation of, given a vertex, go through the edges adjacent to that vertex. And with modern software engineering, I can set it up so that I get them in random order. Now, I can't do it with adjacency lists. Somebody knows a way, given a list, give me a random element in constant time, I'd be happy to listen. But I don't know how to do that. I don't know that you can't do it either. So let's start with that basic problem. But with modern systems, usually you have so-called ragged arrays. So if you have the whole graph ahead of time, you can pre-allocate an array for each list. And then therefore, you've got not linked lists, but arrays. And then when it's time to get a new vertex, you can just add this one-liner to exchange with a random place, and then you get them out in random order. So that's one line change to the code, at least. it turns every graph algorithm into a randomized algorithm, and it gives the very important practical effect of having predictability in performance. No matter what the client does, if I run the things a lot of times, I'm going to get basically the same answer. Now, this is another year down the tubes, I don't know, year, but quite a while. This is full employment for algorithm analysts, because now it's the graph, not the representation, but it's the graph that determines performance. Even for this ST problem, you can figure out, like for this graph here, the average running time for this graph here is going to be a lot different than for that graph or that graph. There's all kinds of traps you can build and so forth. So the graph model is still going to matter a lot. But maybe the grid graph model, maybe that's one at least I can understand. That's still hope. But now at least I got to the point where I know that if I run the algorithm on the grid graph, I'm going to get the same answer, no matter what the client does. I think it's really interesting. I've got even little graphs, like 6-node complete graphs. What's the distribution of the running time, depth first search on those? I don't know. It's got a very interesting mathematical structure. So there's plenty to do in terms of work down there, but let's get back to the problem at hand before I run out of time. So that's fixing depth first search. And I won't do breadth first search because same thing, I'm going to use a randomized iterator. And then finally, let's get to the situation here. So that's breadth first search, depth first search, and union find running on the grid graph. And so now I want some kind of mathematical model for what's going on. Well, for breadth first search, I think I got it. How many vertices or how many edges on the average are examined by that algorithm? How about 3/4 of them? Yeah, just looking at the picture, right? So and that's, I think I can prove that one. Yeah. It's going to be 3/4 for breadth first search. Depth first search, no idea. You saw the paths going. Union find, no idea at all. But now I can run experiments. And by the way, if I had done animations like this, I would have found this problem with the representation really early on. That goes back to what I was saying about teaching the students when they first program. If you've got a reasonable programming model, when it's no work to add an animation like this, then you're going to be better off than if you have to call a graphics guru or take a course in order to do the animation. The difference between writing the code and adding the animation is literally like 3 lines of code in these things. So that's an important point about a reasonable programming model. Okay, but now I can write a different client that instead of doing animations, runs them 1,000,000 times and averages and tell you the answer. I think DFS is the fastest way to go. I don't have an analytic proof of that, but this is using the scientific method. I ran, I think, some reasonable experiments, and I think if you run these algorithms, the same thing will happen. That's the best I can hope to do. Depth first search is going to be a lot faster than breadth first search and union find. And you say, well, and I think it would be cool to try to understand this through analysis, but I don't know how to do it. I say, well, interesting. Before I run out of time, I looked around for a long time. Maybe there's some great faster method. And you came upon this one. How about if you run 2 depth first searches, and then when they hit, you got a path. Do one from the source and one from the vertex. People have told me, oh yeah, we knew this in certain other situations. But anyway, for this particular problem, that's going to make it really quite a bit faster. So it gets down to like 13% of the edges. So that's going to be faster. My program's 10 times faster than yours. It's not log n, so it's not going to be like exciting in the theory literature, but it's going to be 10 times faster. So, but it still seems like it's linear, but I don't even know that. And it seems like you run big ones, it seems to get lost sometimes, but I don't know what the deal is exactly. So I studied for a long time different types of hybrid algorithms, and I'm not going to focus on the details of this. I tried lots of searchers. Best thing is DFS with 2 searchers. tried lots of things. And then I came on the idea of small world graphs. Everybody knows about small world graphs. That's a big new thing lately. Lots of models of small world graphs. In there, the idea is a small world graph has a large number of vertices, got a lot of local connectivity, but it's got low average path length. And people have learned that if you take our grid graph and add just a few random edges, like this is m squared, if you had m random edges, then you get a small world graph. Or actually, if you do that to any graph that's got local clustering. And there's lots and lots of models. Small world graphs are important models of things ranging from infectious diseases to protein interaction and so forth. And I said, well, I've got this code that is model independent. How about if I run it on small world graphs? And I was amazed to find that if I just run my code, I didn't change the code at all I did was put in a small world graph, it nails it. It finds the shortest path in the square root of e steps. It just finds it. So no change at all in the graph model. And not only that, I think I can kind of prove it. Now, I'm not like publishing this as a journal article right this minute, but it's not that hard a concept. Well, first of all, I did lots of experiments, so I'll just have that say it's really fast. But here's the proof sketch. If I start from the source and I do just a short distance with depth first search, I'm going to hit like a certain number of vertices, like square root of e vertices. And if I do the same from the sink, from the destination, I'm going to hit those. Well, but since it's a small world graph, and since I've randomized, those are going to be random vertices. So birthday paradox means they're going to hit. So I have square root of the number of vertices that I've got in each of these sets, they're going to hit, or pi times the square root of it. So I think I can prove that this thing is going to be fast for small world graphs. Very cool, very cool. All having to do with applying the scientific method while studying and trying to develop algorithms. I'm going to back off from the talk within a talk because I have one more point I want to make in my last 5 minutes. But anyway, the lessons from that is don't think that we know much about performance of graph algorithms. We don't. We know a lot about worst case bounds theoretically on performance of graph algorithms, but we don't know much about actual performance. And if you want to know about actual performance, you better implement them and run them and test them against hypotheses about the running time to make sure that you understand it. So the problem is, anytime we've done analysis, and people have been taught it, it seems to require a lot of math. And I can't be saying, does every programmer and every cubicle out there need to know this math? Well, so I've got some news to report. The good news is, first of all, there's lots of people that are working on this. That you may not be aware of that, but there are lots of people working in the right direction. And not only that, we're making progress in that we're getting simple universal models that help us understand performance of entire classes of algorithms. And I'll just quickly try to sketch that for you to finish up. So this started with Knuth. There are appropriate mathematical models out there that we can use for performance. And Knuth's books are all about that. The problem that has come up is that a huge portion of the theory community has backed off into big O type of performance that are inappropriate mathematical models for studying performance. But we've got this other community that's kind of stayed on the course, and let me try to explain what's going on. We now have a modern basis for studying algorithm performance in discrete structures known as analytic combinatorics. The father of this field is Philippe Flageolet and many co-authors, including many on the Purdue faculty. It's based on classical combinatorics and analysis, but it's got interesting twist about universality that I'll try to get to. So it's all about encapsulating sequences with generating functions, about using formal methods to derive generating function equations, and then treating those equations as relationships among complex variables, and using classical complex asymptotics to study the functions and get accurate approximations of the original sequence. Now this requires a lot of math, so bear with me till I get to the bottom line. And I'll go through quickly. There's a lot of math on these slides, but I just want to put them there. I just want to talk about the stuff in red mostly. So in Knuth's time, what we would do is derive a recurrence relation. So this is number of binary trees with n nodes. Get a generating function, multiply by z to the n, and sum over all n. The recurrence relation gives us an equation, this b of z equals 1 plus zb of z squared. That equation you can solve algebraically, and that gives you a solution, what the generating function is. And then you can manipulate that solution, in this case, use the binomial theorem to expand 1 minus 4z to the half, and you get the coefficients back. So the number of binary trees is exactly 1 over n plus 1, 2n, choose n. But that still doesn't help you, like how big is it for n? You need an approximation in terms of standard functions, and we can use things like Stirling's approximation to get computable approximations to the coefficients. The problem with this method is that we basically needed a brand new derivation for each problem. And that's too much of a burden for the practicing programmer out there. And not only that, there's papers out there, 50 papers out there where square root of pi n occurs. Is that a coincidence? It just kind of comes out in the bottom. Seems like totally different problems. Square root of pi n, and there's other examples like that. In the modern world, we do things a little bit differently. So now what we do, this is a different problem. This is number of trees with n nodes. Now what we do is we define precisely what we mean using something called a combinatorial construction. It's kind of like a context-free grammar that describes what is the structure. Along with that description, or definition what that description is, we have a direct association with generating functions. So the combinatorial construction immediately gives the generating function equation. You don't have to mess around with the recurrence and sums. We get them out for free. Still do the algebraic manipulation, but then we treat that thing as a complex function. We don't bother to look at the coefficients. We just want to look at the growth of the coefficients. And there's two basic principles that have emerged, both having to do with singularities of the function in the complex plane. The location of the singularity tells us the exponential growth, and the nature of the singularity gives us the sub-exponential growth. And again, I'm not going to do the math, but just put it up here to show you that classic complex analysis gives us the information that we need. There's a Cauchy coefficient formula about functions in the complex plane having to do with residues that gives us the answer that we're looking for, coefficient of z to the n in this function, as a contour integral around a circle in the complex plane. And you can deform that circle, except you have to watch out for singularities in a particular way. This is actually what Stirling's approximation comes for. And we can get down to the approximation of the coefficients directly without having to know exactly what they are. Having to do with actually gamma function, Euler's gamma function. And that's what square root of pi is, gamma of 1/2. So all of these functions, like birthday paradox, these others, are getting the same answer because they have the same type of singularity in the complex plane. So from that observation, people have realized recently that we can develop universal laws that are extremely general, that derive from this technology. So for example, you could take a sequence of combinatorial constructions that involve each other. It's just like a context-free language, or any Java data type. A mumble is a mumble of mumbles divided by mumbles of a mumble, and you give each one of them, you can have an arbitrarily complex series of context-free constructions. Those directly map to a system of generating functions. Doesn't even have to be linear. We could do elimination on that to get back to a function, and then we have very general theorems that show that they're approximated by simple complex functions around the singularity, and the same answer comes out. We can effectively compute the answer for any context-free construction at all. It's going to be a constant times another constant to the nth power times n to the c. For any context-free construction at all, extremely general. And this is only one of several such laws that have recently been discovered. So what does this mean for the practicing programmer? It means that a good starting hypothesis is that the running time of your program is n to a constant. And so that constant's going to depend on the singularities of the function in the complex plane. You can do the math, or you can just do the doubling test that we taught to find out what the constant is. It's log of t of 2n over n. That's it. There's a lot of caveats to this, but that's how I want to finish is I think that writing a program without understanding its performance is like firing a rocket without knowing where it's going to go. It's like not knowing the dosage of a drug or not knowing the strength of a bridge. There's catastrophic results that can ensue. So I think we should teach the scientific method. We should use it when we're developing software, and we should try to continue to develop underlying mathematical models. And that's my talk. Thank you. Sure. I don't want to like fully frontally assault all worst case analysis. I'm just saying if you're doing worst case analysis, don't try to predict performance without testing it yourself. And that's where I draw the line. Somebody says O of log n is better than O of n squared. If O of n squared is going to happen with probability 10 to the minus 50, quicksort's like that, hashing's like that. We use that stuff all the time. So those are taken out by worst case analysis, but we use them all the time.
That you can point to with big systems where this has worked?
Photoshop. And Photoshop is a huge system. I don't know how many million lines of code. But when you're doing a transformation on an image, that's 50-line module, and it better not be quadratic.
I guess what I'm asking is, you've gotten to the point where someone's looked at this and said, oh, yeah, I can do this. As opposed to...
I'd say the image processing guys, well, they hit it before it got to the customer because immediately the number of inputs got up really high. But I think that's a fine example. They're looking for better performance. They're looking for understanding the performance of the transformations they're applying, and they're not deploying them unless they understand it. No, I just said we should understand performance. And, okay.
But somewhere in the middle, you took what was probably a deterministic algorithm and made it a randomized algorithm.
Yeah, and that might have been a performance penalty.
And so what
you
almost translated that to was saying that for a randomized algorithm, you should be doing average case analysis.
Well, that's certainly...
which said do an average case analysis for a deterministic algorithm.
Well, this particular algorithm has no inputs. Okay, there's a lot of algorithms where I'll say randomize the inputs. So I say that for quicksort. Okay, so that's a deterministic algorithm, but I randomize the inputs. And if you don't understand your deterministic algorithm, it's not a bad technique to randomize it to get predictability. I guess so far I'm along. And if I have one that I don't understand and I'm running it, then I shouldn't be trying to advise people what's going on.
But the point still is, for randomized algorithms, we should be doing average case analysis.
Well,
and that's a point well taken.
Mm-hmm. Yeah, and I think unless you have, let's see, if you have an arbitrary choice to make, you better make a random choice instead. And I don't think very many programmers do that.
Determining whether your experimental setup is actually going to give
Yeah, so that's, is computer science a science? And are we trying to determine something about the natural world or just something about our math? And so what I'll say is we're doing the scientific method to test the mathematical results, and it's perfectly valid to do that.
Okay, well that's a nice example, but do you incorporate it in your courses, and do you have other examples like this that you use to drive the point home to your students?
We do it for every, so that is every assignment. We try to make sure there's a performance component. And if you don't understand the performance of your solution, you're not going to complete the assignment.
I guess what I'm
So,
emphasizing is more this question of reproducibility, understanding that you've got a decent experimental design.
yeah, I'd like to do it more. I'd like to do it more. People ask that, but the fact that I'm doing it all is kind of heresy in a lot of computer science circles. They want to focus on the program being correct and lots of other things before they get to performance.
What is the cost of introducing randomness?
That's a potential problem, and I usually get hassled by systems programmers types on that. In fact, there's a famous story about Quicksort. The Bell Labs guys would not put randomness into Quicksort because of the performance cost in the initial implementations of QSort. And they got burned. They turned out to be quadratic. And they had users that found it to be quadratic.
You're
Yeah.
also telling us that we don't understand how to generate random numbers.
Yeah. I worried about that for a while, and it's definitely a flaw in my argument. So I'm saying for Quicksort, well, they don't have to be totally random. Actually, the bad one will work fine in terms of performance. I can run experiments where I can't see the difference between truly random and bad random for Quicksort. Yeah, I'm not insisting on true randomness, and that's a hole in my argument. The other example is hashing. Most systems use hashing. Hashing, in order to believe in the performance, it's got to be the case that every input maps equally likely to every output. But so that means you have to have a great hash function for every data type. Actually, the default hash function in Java is the address, machine address of the thing. So you're not even defending it, that's total arbitrariness. And so if you're using hashing, you better be prepared to implement at least a decent hash function. And Java also got burned on strings because Java, first implementation of Java, they took every 8th character. And then they got customers calling up saying my search is going quadratic because actually most of the things they're running are pretty regular and they were missing the difference.
So I think that's an important point here. I mean, one has the same. One type of doing average cases is randomization. You introduce randomness in the algorithm.
Or you can randomize the inputs.
Right. Or the input itself is drawn from a problem.
Yeah, you can make the assumption that I believe that the inputs are random.
So for that, I mean, your paradigm is like, because if I know that the graph is a random geometry graph or something like that, then I can come with better algorithms.
You don't have to use the randomized iterator, maybe.
I also come with faster algorithms, which are taken into that.
I'd love to see even one example of that. So, you can come up with a predictable, fast, general-purpose algorithm on graphs. Yeah, people do work on these things, and I don't want to. But yeah, that's a fair point. That's a fair point. I guess the main point I'm making is all that's fine. Just give me a hypothesis about the performance, and give me a test that validates that hypothesis, and then I'm happy.
So all I'm saying is,
that's the top-level point I want to make.
assume the distribution like the random geometry graph, you can come up with nice algorithms. I have done that in many.
No, I didn't assume what. But did you? But,
They're not general purpose algorithms. They work well for this.
yeah, that's okay. So then you're in good shape. I'm just saying there's a lot of people out there that are not doing that. And it's true that you're a person that's much closer to practice. I gave you my leading theoretical computer scientist. I went to a algorithms conference. And I was on program committee. Not a single person had implemented their algorithm. 100, 200 papers. What's going on there? And they're not, it'd be fine if they were saying, we don't care about applications, but all the papers say, oh, it's extremely important in these 19 applications to do this. But not a single one had implemented the algorithm. let alone formulate a hypothesis on its performance and test it.
Let's thank Prof for the inspiring talk. Thank you. Thank you.